Hey everyone, I hope you all are doing good. So in this lecture, we will be covering inclusion and exclusion and the tree diagrams, right? This is going to be like a very easy concept to understand. So I would say you can even like fast forward it, but super easy concepts to understand, right? So let's just do a quick recap. If you remember in the last video, we covered the product and the sum rule, right? Let's take a look at the sum rule once again. So if I give you one of the questions, right? If I tell you, let's say, uh, you have 4 shirt options, or you can choose from 3 pant options, right? Let's say you're going to a market and then I give you these options. So I ask you how many total options you would have. You would have 4 shirt options plus 3 options from the pants, right? Now let's say I ask you, let's say you're taking a course, right? Let's say um, from computer science and computer engineering. Let's say I ask you to choose one of computer science or computer engineering, right? And then I say computer science has 5 courses and computer engineering has 5 courses, but they don't overlap, right? So that would mean total number of 10 courses are there. So you could either pick 5 courses if you're taking computer science, or you could pick 5 courses that are in computer engineering. But if you remember in the sum rule, the most important part was that there was no overlap, meaning whatever the options I was giving you, right, they didn't have any overlap. Like the shirt and the pants, they don't have any overlap, right? But now think about this, right? I tell you, you have to pick a computer science or a computer engineering, right? And computer science has 5 courses and computer engineering has 5 courses again. But the 2 courses in both of these, computer science and computer engineering, are the same. So now in this case, what would be the count? And that is exactly where the inclusion exclusion principle comes in, right? Very simple to understand. Okay, so let's just take a look at, let's try to remember one more thing from the sets, right? If you remember for 2 sets, if we take a union of 2 sets, right, and try to count down how many elements are there. So let's say A has 5, count, wait, let's say number of elements in A equal 5, right? Let's say A has 5 elements, number of B equal 6. So let's say A has 5 elements and B has 6 elements. Now, I hope you guys remember that these lines around the sets basically represents the count, right? Or the cardinality, I should say. Yeah. So if you remember, if I take a union of these two, then the union is basically the number of elements in set A plus set B, and then we subtract whatever is the common between them, like whatever is the overlap between them. And this formula over here is the one exactly what we will be using for our counting too, right? So just like I said in the example of, if I ask you the question, right, I ask someone to choose, you can either choose computer science, which has 5 courses, or you can choose computer engineering, which has 5 courses, but 2 of the courses in both of these fields are overlapping. So how many total options you would have? You would have 5 plus 5, 10, but then you would also have to subtract the overlapping courses, which would be 2 in this case, right? Okay, so I'm not, if you couldn't understand by the way I'm saying, let's just try to understand with this example over here, right? Okay, in a class of 40 students, 25 are in the math club, 18 are in the science club, 10 they say are in both. So 10 students are in both math and science club. Now think about this, right? If, let's say, let's look at the question, how many are in at least one club? Now, if you just add 25 plus 18 together, right, that would be a mistake. So 25 plus 18, this would be wrong. And why? Because think about this, right? There are 10 students that are in both of these clubs, so you would be double counting them pretty much. So what do we do in this case? We use this rule that we have over here, right? So it's pretty much, okay, let's say 25 students in math club plus 18 students in the science club, and then we also need to subtract the ones that are common in both. So that's going to be 10 in this case. Okay, and this would be our final answer. Okay, now the next question is how many are in neither of the clubs, right? So how many are in neither? This would simply be, okay, So you have 40 students, 25 are in math club, 18 are in science club. So how many are in clubs in total? That would be this amount. So how many are in neither? You would simply subtract 40 minus whatever this amount comes down to be. So it would be 25, I should say, I can just simply write it as 15 plus 18. And that would be the total number of students that are in neither of the clubs, right? Okay, so I hope you were able to understand this concept. This is not like very tricky concept to understand, especially for like when you just have two options to understand. The idea is very simple. Problem is, if there is some sort of overlap in the options you've been given, and then you're trying to count it down. The problem is that if you don't remove that overlap, you would be counting it 2 times. So that's exactly what we do is, okay, 25 in math club and 18 in science clubs, there is some overlap happening because they mentioned that there are 10 in both. So what I would have to do is I would have to first add whatever the elements are in the sets, math club plus the science club, and then subtract down whatever the overlap is happening, right? It's like very basic math in very simple terms, right? Okay, now let's take a look at the example where you have 3 sets and there's an overlap happening in the case of 3 sets, right? That is like a more difficult example to understand, but that should be fine as well. Okay, so let's understand for 3 sets. Given you have A union B union C, and you're trying to find the amount of elements in A union B union C, what would be the formula, right? So the formula is given over here. It's pretty much in order to find the count or the cardinality of 3 sets, of the union of 3 sets, what you do is you first add them individually together. You subtract the intersections of the pairs, and then you add the in the intersection of all 3 sets together, right? Now, I'll try to just quickly explain the meaning of this formula. Like you can easily like remember this formula. It's not that tricky, but I'll try to explain the reasoning behind this formula, right? Look, it all comes down to pretty much the logic. Like what we're trying to do is we're just trying to not count something extra or miss anything, right? So I've been given 3 sets, A union B union C, and I'm supposed to count the total number of elements in them, unique elements, right? Now, I want to prevent that I don't miss anything, and I also want to make sure that I'm not counting something 2 times or 3 times, right? So think about this. First thing I did is I count down all the elements that are in set A plus set B plus set C. So now I know that something is in set A, set B, set C. I've added all those together, right? But that could be wrong because maybe some elements could be in A, B both. Maybe it could be B in C, or maybe they could be in all 3 of them, right? So what I do is first let's subtract all the pairs. So I removed all the elements that might be in A intersection B, right? Let's just remove them together. Okay. Now, second is subtract whatever elements are common in B intersection C once, so that the count is correct, and remove it once again from C intersection A. So now whatever was common in A intersection B, we have removed it once. So if it was double count, we made it the right count again. Same thing for B intersection and C intersection A, right? Okay, now let's understand why do we add A intersection B intersection C again. Now think about this, right? If some elements were in all 3 of these sets, then we added, let's say wait. So let's say some element is in all 3 sets, right? Let's say it's in A, B, and C. Okay. Now the point is, that means when you subtract A intersection B, you would subtract it once. So first, let's say it's in A, B, C, you add it 3 times, right? This would mean you added it 3 times. Okay. Now when you subtract A intersection B, B intersection C, C intersection A, you do -1, you subtract it once, subtract it again, subtract it again. So what this means is you added it and then you subtracted it again. So that means you never really counted it. This would mean 0. So at the end, what I have to do is I have to count it once again, and that's why we are adding this term, right? Okay, so just once again, quickly, right? My entire point is, my entire goal of inclusion-exclusion principle is that I have been given some, I need to find the count of some combination, right? Or some sets. The problem is that I need to make sure there's no overlap happening, right? Meaning I don't want to count something extra in the case. So for that case, I had to find the formulas. For two sets, it's very simple. It's just that you add the amount of elements in two sets, subtract what's common in between them. For three sets, the formula is kind of a bit more tricky, which is, okay, I add the elements individually that are in all the three sets. I subtract whatever is common, what could be common in the pairs of sets. But when I do that, I'm removing the elements that are common in all three sets. So I need to add all those together once again at the end, right? And that's pretty much the inclusion-exclusion principle. Now let's move on to the tree diagrams. Okay, guys, let's understand the tree diagrams, right? Now, this is going to be a very important concept once again. This is more like you don't usually use it, but for like very small examples, it's very, it kind of helps out a lot. And it's not just limited to discrete math. Once again, even personally, I've used it a lot of the times in solving like leet code problems or other sort of coding problems too. This tree diagrams really come in handy, right? Okay, so it's basically a visual way to count, useful for very small cases. So let's just try to directly do it with a very small example, right? Okay, how many 3-bit strings have no consecutive ones? Now, obviously, you can use the formula way to solve this problem, but we will try to solve this problem using the tree diagrams, right? Okay, so I've been given how many 3-bit strings, bits meaning 0 or 1. Okay, how many 3-bit strings have no consecutive ones? So the question is that, okay, you need to find 3-bit strings, the count of 3-bit strings where ones don't come together, right? So it could be like 1, 0, 1. It could be like 0, 0, 1. But you can't have like two consecutive ones together, right? Which is going to be something like, if I have 1, 1, this would be incorrect. Basically, ones can't be consecutive, right? Okay, so let's try to do it with a tree, right? Okay, first of all, I'm gonna start the tree. Okay, so in the start case, in the beginning, let's say for the first position, right? For the first element in the sequence. So we are over here for now. Let's assume that. Okay. Okay, in the start position, you can choose any of the two values. You can either choose 1 or you can choose 0. Okay, so now let's move on to the second step, right? So I hope this makes until this point. For the first step, I'm just going to mark it 1 and then 1. Okay, so I hope this kind of like makes a reference to this pretty much. Okay, now at the second step, think about, let's say if you chose 0, what happens, right? So we're going to make a tree. If my choice is 0, what would be my next choice, right? And if my choice was 1, then I would make the tree further down in that, right? So it's pretty much that, it's kind of like, think about this, right? You're extending a tree down until you've reached the final point. Okay, so if I chose my first digit to be 0, I can choose the second digit to be 0, right? And I can choose the third digit to be 1, right? That's totally fine because I just don't want consecutive ones, okay? But what if I chose 1 in my first position, right? In that case, I can only choose 0 as my second option, right? Try to pause the video if this doesn't make sense, but I'll try to explain it once again. Question is asking that 3-bit string with no consecutive ones, right? Okay, so we started the tree down. For the first case, we have two options, right? I can either choose 0 or I can choose 1. Okay, that's totally fine. Let's say in the option I choose 0, for the second place's option, so this would be like the second place. For the second place's option, I can choose either 0 or 1, right? That's totally fine. But what happens is, if I chose 1 for my first position, right, I cannot choose 1 in this case. That would be wrong. Why? Because we can't have consecutive ones. So only option I'm left with would be 0 in that case. Okay, so I hope this is making sense until this point. So now for the final one, okay, so let's say if your first is 0, second is 0, then what are the options for the final one? You can either choose 0 or 1 again, right? I hope this side of the tree makes sense. Okay, so let's say now if you chose 0 as your first character or first bit, 1 as a second bit, now once again you can only choose 0 as a third bit, right? Why? If I had like 1, that would be that would make this string over here, and that would be incorrect, right? So I can only have 0, 1, 0, or like a bit string where 1 is not consecutive. Okay, so I'll just try to quickly draw it once again. Okay, so start 0, and this is done. Okay, now let's say for this side of the tree, you chose 1. For the second one, you can choose 0. Now in this 0, I can choose either 0 or 1, and that's going to be totally fine. Okay, so I hope this kind of makes sense, like you were able to understand exactly what I did. I'll just give a quick summary once again. So I was supposed to find okay, so my goal was to find how many 3-bit strings have no consecutive ones, right? Okay, so I made a tree. I'm using the tree diagram formula. First option in the first place, I could either have a 0 or a 1. Okay, now let's bring the tree further down, right? In the second step or in the second stage of the tree, for 0, I could either have a 0 or a 1. That's totally fine, right? But for 1's case, I could only have the value 0. Okay, when now further down, if my second value is 0, the final one could be 0 or 1. But if it's 1, then it could be 0, right? And if the second value is 0, then it could be both 0 or it could be 1, right? So how many total bit strings I would have? Let's just count it together, right? So 1, it could be 0, 0, 0. Second, it could be 0, 0, 1. Third, it could be 0, 1, 0. Fourth, it could be 1, 0, 0. And then finally, it could be 1, 0, 1. So it would be 1, 2, 3, 4, and 5 in total, right? So 5 would be our final answer. Okay, so I hope you were able to solve, like understand the tree diagrams. Now I'll be giving 2 questions on the board, and then we will move on to the next lecture. Okay, everyone, I've given these 2 questions on the board. I think super easy to solve. I think second one is a bit tricky to understand, but try to pause the video, solve these questions, and then I'll solve them on the board. Okay, so I hope you were able to solve these questions. Let's just solve the first one. In a group of 100 people, 60 speak English, 45 speak French, 20 speak both. So how many speak at least one language? The answer would be very simple. So it would be set, let's say this is set A and this is set B. What would this be? 20 speak both means this is A intersection B, right? So my final answer would be A plus B minus A intersection B, which would simply be 60 plus 45 equal 105 minus 20, which is equal to 85, right? So I hope you were able to solve this question. Now, second one is a bit more tricky to understand, so I would say like just focus a bit. Okay, how many integers from 1 to 1000 are divisible by 3 or 5, right? Now, we have a or in this case. Okay, so first of all, 1 to 1000 is like 1000 numbers, right? That's pretty simple. Let's figure out how many would be divisible by 3 first, right? Just the simple part. So if I need to find all the numbers that are divisible by 3, I need to find, I can just simply do 1000 divided by 3, right? Which would give me almost 3.33, right? And I would have to floor it. Floor meaning that floor basically means if it is a decimal value, you go to the lower side of the decimal point, right? So this flooring would give me 333, and this is the exact number of values that from 1 to 1000 are divisible by 3, right? So 333 values, meaning like 3, 6, 9, 12 until 999, there are total 333 values, right? So this is divisible by 3, and then how many are divisible by 5? Once again, just simply divide it by 5, a 5 over here. This would give you 200 values. Okay, now once again, right, there's a or in this case, and you need to understand this. This is not just the basic sum rule that we can apply, right? And the simple point is because there is some overlap too. There could be values that are divisible by both 3 or 5. So now let's try to find what are those, the count of overlap values. So in order for me to find the amount of overlap values, how about I do this, right? I know that in order for me to find the overlap values, I can simply first multiply 3 by 5, giving me 3, 5, the 15. So whatever values are divisible by 15 are going to be the values that are divisible by both 3 and 5, right? I hope that kind of makes sense. This is basically the LCM of 3 and 5. So, but the basic idea is, okay, I need to find values that are divisible by both 3 and 5. If I multiply 3 and 5, that gives me 15. If anything is divisible by 15, it has to be divisible by 3 and it has to be divisible by 5. Okay, so if I do 1000 divided by 15, this gives you almost, this gives you 66. So 66 values are going to be the one that are going to be divisible by both 3 and 5. Okay, and now in order for me to find the final count of integers, I simply do 333 plus 200, subtract the 66 from it, and this would be our final answer. Okay, so I hope you were able to understand this question. If it was kind of tricky, I would say pause the video or like take a step back and then get back to the question. But the point is simple. We first found all the count of values divisible by 3, then the count of values divisible by 5, right? And then what we also needed to find is, since we know there's an overlap, right? Meaning there could be values that are divisible by both 3 and 5. We found those values too. And how did we do that? We did 3 multiplied by 5, giving us 15. And dividing 1000 by 15 gives us values that are divisible by 15, or in other words, divisible by both 3 and 5, right? So, and in the final case, just add divisible by 3 plus divisible by 5, subtract divisible by both, giving you the final answer, right? Okay, so I hope you were able to understand this lecture, and now let's move on to the next one.